Greetings, fellow travelers. Your mad scientist is here. Or not. Anyway. Music's cranking a little bit here, ain't it? We'll crank it down just a little bit here. Also, my illustrious pictures going here. I gotta just update my stream here a little bit here, somewhere wherever it is. Seem to have lost it. Yeah, right here. We're going to talk about my little project. Oh, why did the mouse do that? It's not a little project, believe me. And I'm not going to give out like all the details. We're going to talk about a little bit of history. We're going to talk about a little bit of mystery. We're going to watch a few videos and talk about a little bit about how light is created and that sort of thing. And we're going to talk about my understanding and my belief, which are kind of two different things. We all have beliefs. We all choose to have beliefs. We all choose to have certain types of beliefs and that kind of thing. I'm respectful of other people's beliefs because of the photon, believe it or not. If you watched my last discussion on photons explained or light explained or whatever it was, I forget. I have short-term memory issues, but what did I just say? Okay. You will recall that it took a whole bunch of photons to come together and have a party, and when they got to the end of their journey, they created a picture. So like one photon is a piece of a puzzle, but it's a very strange piece of a puzzle because one photon has all of the information of the puzzle, and yet it is only one puzzle piece. I watched another video today. I don't know, there's strange things happening. Okay, I'll tell you about that belief system of mine in a minute. They said someone had set up an experiment where they could create one photon at a time and shoot it out of a gun, like an electron gun or something. And they claimed that the photon had to go through two of the slits at the same time. Now, my first immediate thought was absolutely not. That's totally impossible. In our physics, let's just say. So they sort of proved it wrong. So they sort of proved it wrong by saying that they created a monitor on each slit. And what they discovered, this is like recently, what they said they discovered was that while you're monitoring each of the slits, the pattern that came out was only the pattern from the two slits, not the multiple pattern that they were talking about and that normally happens. That inference, that so-called experiment, which I'm definitely going to see if I can try to replicate, said that the photons acted differently when they were observed. Now, as I mentioned before, the photon carries all of the information from where it came from. So when it is interacted with, perhaps it picks up new information and totally forgets the information that it had when it left its source. So in other words, when it reaches the slit, it now has a new source, and that source is the slit. But it's only a receiver. The device that's monitoring what's going through the slit is a receiver. It's not a transmitter. So a receiver in and of itself cannot directly affect any waveform, any particle, or anything. It just sits out there and receives something. Well, now, actually, that may not be true. You have to have, let's say, for example, an inductor, and you put an inductor out there and you use it as a transducer and it picks up some information. Well, that inductor has currents going through it, and it is interacting with the information that's coming into the inductor. So in a sense, there's an interaction there. It's at the end of the particles travel, and so perhaps the particle releases all of the information to that inductor. It's interacted with something. So it's possible that the device that they use to interact with the slit, monitoring the photon, interacted with the photon, and the photon released its information from the source to the detector. So in an effect, its journey had been completed as soon as it reached the slit, because the slit was monitored. Now, I'm going to go ahead. Well, no. Okay, so that was that aspect. And they said, well, if you observe something, then it changes the results of whatever was happening. It may not change the result. It may end the result of where the photon's information may have released its information at that point. So it didn't really change anything, maybe. It just, the photon, maybe the photon's very sensitive to outside conditions and, that kind of thing. I would agree that a photon would be very sensitive, or an ion, which is like a free charge or something, sitting out around there is looking for something. It's looking for a positive charge or a negative charge or whatever it is. It wants to get together and have a party. Nobody likes to be alone. Nothing likes to be alone in nature. It is impossible to survive alone. You have to have something else to survive. You gotta have food. Food comes from somewhere. It's a cycle, It's called the life cycle. If we didn't have it, we wouldn't survive. The life cycle is a paradox. Where's the beginning? Where's the end? There's all these questions. So there's a history and there's a mystery. And I can dive in. I want to dive into that a little. If this thing ever... Yeah, okay. So, alright, that's muted, that's paused, that's muted. Alright, so I'm gonna drop that, and I can see what's happening on the stream. So there's a history and there's a mystery. Did I make the name of my stream correct? I think I did. I don't remember. Yeah. So I'm gonna call my project ITC Lightwave. So, many years ago, 20 some odd years ago or more, I started this project as a means of connecting dimensions to in an attempt to contact beings or entities from other dimensions. Now, if people watch my stream long enough, they will pick up this information. It's not something that I normally just come out there and talk about, because for the most part, people think, oh, you're crazy, you don't know what you're doing. People have tried this for years and years and years, and we got a bunch of people out there faking things, faking pictures, faking voices, just faking everything. Misinformation. It's even worse than that. It's not misinformation. It's literally, it's like a cult. It's like people are out there thriving on misinformation and selling it and making money off of people that are so innocent, that they'll what is the word I'm trying to think of? They believe anything. Gullible, we're all different. We're different, and over the years, people have changed, and we've become a little bit more enlightened. I would like to think. Now, if you look at this picture that's on my stream, it shows this person or being in a state of possible transcendental meditation. I don't know why. Yeah, there we go. I thought that was Anubis over there on the left, but it's not. So, you see a pyramid. Now, I'll tell you right now that whoever made this picture, this AI or whatever, that pyramidal structure is not the shape of the pyramid in Egypt. It's a little bit too, the angles of the sides are too steep. I've studied a lot about pyramids. I've studied a lot about different civilizations, Sumerians, Egyptians. I believe that we have been visited by beings from other worlds physically, and I believe that those beings have left us technology far in advance of what we would have had if they hadn't arrived. And maybe they've come back and we've picked up some information, and whatever the reason, there are certain laws of physics that can't be transcended, and space travel is one of them. Now, they talk about wormholes and string theory and all kinds of weird stuff. But if you're in a faraway place, how is it that you're going to create a wormhole from wherever you're at to the planet Earth? You can't transcend. If the wormhole was already there, you could travel, or maybe civilizations were able to create a wormhole between living existences, and as time went on, they passed away and they left that information, and maybe they completely got obliterated or whatever, and so that information was left behind, and it was discovered by other advanced civilizations to use that technology to travel the universe in instances of time that are totally, you don't know how they did it, It's like this movie, Contact, where they said, okay, well, we've been traveling these wormholes for thousands and thousands of years, and they say that's just how it was done. Nobody knows where it came from. Personally, I hate to say this, but I don't think we're in that state of existence. It's a possibility. I studied Richard Feynman's physics a little bit, and I believe in possibilities. Why would I even be doing something like this? I could rant forever, once I get talking. Okay, I got a drink here. Gotta make that noise so it tastes better, So, The Egyptians talked about certain aspects of life and death. I believe some of those aspects may have been literal, maybe some of them were not literal. They had meaning, like certain religious texts will come out and say something that has a meaning, but you can only understand it if you read between the lines. Outside of a religious or cultist context, there is information in religious texts that has to do with multidimensional travel and communication and reincarnation. All of the things not of this world, not of this time, not of this space. Why this information has all been handed down in riddles and in stories. Maybe that's just the way that information was given out hundreds and hundreds of years ago, or 1,000 years ago. Maybe they felt that the information was too sensitive, too dangerous, but there had to be a record of it because they got the information from these entities, and it was like sacred, you know. So what came along was what's called ITC, which is Instrumental Transcommunication. And there's a website which I discussed in my previous stream, maybe, I don't remember. It's called worlditc.com. Okay, you go there, you see a small group of researchers. They did a lot of research to try and connect what they believe was talking to spirits that had passed on, with devices like video cameras feeding back into TVs, using tape recorders, just a basic tape recorder, a handheld tape recorder, to speak to it and talk to voices and get voices to come back, you know. I believe that over 50% of all of that information was faked. I also believe that there are parts of that information that was not faked. I believe it was real. Why do I say that? Because I have experienced things that I can't understand, so much so that I stopped my research for literally months and months and months, even years, because there was something me as a normal person could not explain. A normal scientific person could not explain how this happened. A voice that comes onto the tape recorder and it precedes the words that you say, and a female voice at that, was a little bit shocking for me. I couldn't handle it at the time, and I had other responsibilities in life to deal with, and I said, hey, you know what? It wasn't the right time for me. I thought that there was going to be a point in my life that I never would have another opportunity, and certain aspects of life seem to happen one way or the other, and opportunities present itself, and you got to ask yourself, this has got to be it, you know. All of my research and all of my information and my tons and tons of papers and stuff that I wrote on particle physics and electronics and linear systems, my knowledge of math, my knowledge of computer science, computer programming, my knowledge of astronomy, microbiology, macrobiology, the micros and the macros of life and the mystery of the universe. Stephen Hawking, Richard Feynman, Albert Einstein, Thomas Edison, Nikola Tesla. The list goes on and on and on. These geniuses, Enrico Fermi, these geniuses did not um, I think they were gifted. I believe in the fact that some people say, okay, nobody's gifted. We just learn this information and we become either really smart or we just become a normal lay person and, we let everybody else build our universe for us. Look at the cell phone technology, the internet. Everything is advanced so much so fast. Now we are actually growing integrated circuits. It's called nanotechnology. And they're using certain types of science in order to grow the circuits instead of build the circuits and then place them on the CD-ROM, the disk, CD-ROM by layer technology, using electron microscopes. They would design the circuit, and they would build the little chips with, like, there's integrated circuits. They have millions, not hundreds, not thousands, not 10,000, not 100,000, a million transistors. Why do you need that many transistors in an integrated circuit? This is a problem for me. And I believe that the circuit that I had built some years ago, I used a candle flame and I was monitoring two polarizations of a candle flame. And I converted the light into electricity. And I was listening with just an earphone coming out of the integrated circuit. I didn't use an amplifier. All of a sudden I hear this religious radio station. Even clearer than I'm talking, because I can't really talk that clear. And it lasted, I don't know, maybe half a minute. And I was like, what the heck is going on here? All I got is a transducer and an integrated circuit, like one little chip. Okay, it wasn't an IC chip. And I get this radio station. So I'm thinking, like I said, these ICs have quite a few transistors built into the IC because they there's modeling going on. So it's very possible that somehow the transducer turned into an antenna and it picked up a radio station somewhere. I couldn't communicate with it. That's another little question here about this whole project. And I still have the components, but I disbanded the project, and it was too sensitive. I was just moving this transducer around and I lost the signal, I was moving it with my hand. And so I've got this opportunity to build something of a similar nature in such a way that now I don't have to move it with my hand. I can use a threaded screw with some gears, and I can move that nanometers in distance. And I have to be able to do that if I want to succeed with this project. And I'll talk about that later. But so yeah, ITC Communications, worlditc.org, not com, it's .org. And you go to that website and it'll explain to you everything about what I'm doing. Now, I've done things with some tape recorders, I've done a few things with magnetics, some electrostatic stuff. There's a couple of theories. There's one theory that the information comes in the form of scalars and not vectors. So a vector has like 3 dimensions and it has a velocity. A scalar doesn't have the velocity, it only has direction or something like that. I don't really remember, and I don't really care about that. I don't have to do the math. All I have to do is build the equipment. And so a scalar is received by something like a Fresnel. It's a type of lens. So I'm assuming that the information coming into this Fresnel is collimated. Now, I am being a little bit forward in my communication on the stream because I'm not going to go into all the whole details. What collimation means, it takes a beam that's spreading outward like a cone and it makes a straight line out of it, something like a laser, you know. So that's that part of it. That's the history. There's a little bit of the history. You can do things like listen to water, watch the ocean, take pictures of the ocean, take pictures of the clouds. There's a terminology, there's a term that's called paradomphia or something. I forget what it's called. But you can look at something and see something, and another person can look at the same thing and they see something different. In other words, you see what you want to see. You hear what you want to hear, etc., etc., etc. This is where observation may cause a problem to collect the information, because once you observe something, that's it, right? Whatever photon or information has received by you, that's it, it's all done. If you use an electronic device, it has to be at the end point of what's going on. Well, if you send a light wave into a slit and you don't monitor it, and then you send it somewhere else, and say into a prism, now what's happened? You send a light wave into a grating. The grating itself could be the endpoint. We can monitor the grating. We can monitor the prism. The prism spreads out the light into different colors. What else does it do? Is it possible? Do we have to have the slit in order to pick up the information? If we just look at a light with no slit, maybe we could collimate it. Maybe not. What if the photons reach a lens and they say, okay, we've reached the end of the line at the lens? Then by the time the information gets to the receiver, the information's already gone. It was left inside the lens. But now you've got new information that's coming out of the lens. So in a sense, the lens could act as a transducer. In a sense, the lens could act as a new source. I don't believe that's possible, okay? Because you could have a certain type of light source, and you can put it through optics. And no matter what you do, you will always get the same information. You will get the information of the source. So that tells me something. So what happens if we monitor the slit and we know that the source is a UV line, and then we try to measure it at the end? Are we going to see the UV line? Okay, that would be a way to solve the question of whether or not observation causes an effect. I have a very big problem with that. So that would be a very good experiment to try. And I think it's a very valid experiment to try and see if that works, you know. I think that's something I'm going to do. I'm going to incorporate that into my design. Maybe not even have the detectors at the slits. I don't know how I'm going to create the input of my design yet. I'm just going to go into the basics of what it's all about. I was watching a bunch of games and stuff, and I'm like, I can't play this game because I need to work on my project. I need to be a little bit more focused with this project. So, with that, we're going to disband with the music. We are going to move this That conversation was a little bit ranted, wasn't it? We're going to remove the picture. Now I'll show you a little bit about my background, and then we're going to go into, what is this here? Oh, I haven't brought it up yet. That's probably why. Where's my video? I can't see it. I got this thing on the other. All right. So I'll just kind of go over this again real quick. So in the background here, you can see that I've got oscilloscopes. This is like my living room, a quarter of my living room. I've got oscilloscopes. I've got frequency generators. I've got frequency meters. I've got voltmeters. I've got more generators. I've got probably 4. I've got a slightly massive square wave generator. I got another generator that generates all kinds of waveforms. I've got 2 other generators that generates waveforms. I've got an attenuator, which is extremely, extremely important. That attenuator goes DC to 300 megahertz, or something like that. At least it covers the audio range. And I got the 3 scopes. They go up to 20 megahertz or 30 or something like that. So I translate RF signals, Lightwave signals into audio signals, and the audio signal is a representation of signal to noise ratio. It's a representation of information. So getting back to my project, the project name itself, I call it ITC Lightwave, because ITC, instrumental transcommunication, is using electronic devices to try to collect information or speak with beings and entities from other dimensions, or spirits that have passed on. They're in other dimensions, so on and so forth. That is sort of my end goal. Now, first and foremost, and the reason for the stream is in science and technology, is because I'm a very scientifically oriented person. I do understand a little bit about the observation versus effect type of thing, and I'm aware of that stuff. And I have started working on the physical aspects, the mechanical aspects of the project. And I will get into that momentarily. I don't want to be at this too long, because I might want to shoot some pool on a game, on a computer, to unwind. But I've been very busy polishing the insides of a couple of computer cases. I've cut the computer cases in half. They are going to be used as an enclosure. The computer cases are made of aluminum and maybe some other alloys. I've got an aluminum plate that is going to slide in and out of the enclosure. The aluminum plate will have all the optics, will have optics stuff on it with sampling. It will have sampling particles, crystals, various objects. Lights will go into these objects and bounce off, and we'll be able to look at the light as a result of that. And what I can do is what I'm going to be doing is I'll use a laser to calibrate all the optics. And there's going to be 2 sections of this device. The first section is going to be very reflective. So when the light goes in there, it's going to have an opportunity to bounce off the walls. It's going to be bouncing all over the place. Then it can be redirected into mirrors, where the light will be split into two separate distinct waves. And each of those waves will go into the next section of the device, which is called the darkroom. The darkroom is where the spectrometer is going to live, and that will be used to calibrate the light section of which is kind of interesting, because when I first was going to do this, I was going to build it slightly larger and have nothing but a light section. And then, not only that, I made a mistake cutting up one of the computer cases because I cut the small one instead of the two of the big ones. And I discovered that the big one is this. Wait just a minute here. I think, yeah, it should be a little different there. I can see my glorious me here. So then I thought, well, okay, so I'm going to use the second computer, the cut-up computer case, as my dark room for the spectrometer. And I was thinking I was going to have the spectrometer in the light room. But then I thought, okay, no, I need something different. It just kind of popped into my head, which is really weird because I was really intent on building just a light area of the project. And then I was going to build a spectrometer outside of the project. Well, now I'll have like a wall between the two sections, and the light that passes from the light to the dark will be like through a small hole or whatever. It'll be focused and collimated. So there's two main reasons for the two sections. And the biggest reason is called noise temperature, that sort of thing. So when you have the light section, you've got all this light bouncing around, and there's some things that are coordinated, there's some things it's not. It's kind of a chaotic, it presents a chaotic nature. And a chaotic nature also presents more noise. Now, I will also incorporate a way to heat up and a way to cool down the light section. It just so happens that I've got an incubator. I may be able to move the incubator into the light section of that case and just take it apart because I'm not using it anymore anyway. I could use that as a heater. Well, actually, no. I've got a better idea. Actually, it's not a better idea. Come to think of it. Yeah, it's a safer idea, is to use my thermal resistors and just put a little bit of excessive current through it, monitor the current, make sure it doesn't blow up the source and whatever, and use the resistors as a way to heat up the room, the enclosure. I'll have a fan, and I could probably, I've got thermistors. I'll probably have some thermistors placed around in different strategic locations in the enclosure to measure the temperatures in the different areas of the enclosure, so that when I heat up the room, that the temperatures will stabilize and they'll all be kind of at an equilibrium. I could probably, maybe what I could do is even still, if I connect a heater up to a heat sink and then use the heat sink to transfer the heat to the enclosure, there's still going to be a central area of heat, and it's going to radiate out in a certain pattern, whereas most of the heat will be kind of in the middle. Maybe that's a good idea. I could put the heater in the middle of the side of the enclosure and let it, go out radially, type of thing, and then I could have a fan. There's different ways to circulate the heat. So heat, what that does is going to add. If there's a certain amount of circuitry inside, maybe that's going to cause some extra noise. I want that to happen. I want that noise. And then, when I turn the heat off, it's going to take time for those things to cool down to normal temperature. And unless if I have a way to supercool the enclosure, which I'm going to use a Peltier circuit to provide supercooling, and I'm really, 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 really hoping I can get that enclosure down to minus 30. That's minus 30 degrees Celsius. I need to go to bed. I got to do more polishing of those enclosures tomorrow, if it's a good day, I hope. I need a way to cool it down below room temperature, because that will give me more headroom for listening to any information that comes in from the light waves. You know, the supercooling is just a thing. I'll also have a way to put smoke into the enclosure, probably like, well, of course, you know, maybe the smoke's not a good idea, now that I think of it, unless of the, because some of the materials inside the enclosure are going to be very sensitive to dust. And I don't want dust to accumulate in that room, so it has to have, it may have to have this continual circulation of air to keep the dust from settling, which is something I really didn't even think of. Most of the mirrors are going to be pointed sideways. Some may point up, some may point down. I'm thinking I'm going to have the cooler on the top, or I could have the cooler on one side and the heater on the other side, and have another fan on the top of the unit, which is very possible, so I can vent the temperature out of the room a little quicker. I'm not really 100% sure about that system yet. Maybe it needs to be on the end or something. I don't know. I've got a space on the end where I can do that. So, as you can see back here, this is my lab. This is where I'm going to be doing all the electronics, all the working with just the electronics. The mechanical stuff is, I got some things that are a little bit too big to put on the bench here, and so I'm going to take pictures of those as I kind of go along, and make sure that the mechanics of everything works. I do have an aluminum plate that I have to do some work on. I'm gonna go into that design too. So, okay, so anyway, before we get into the actual discussion about all this, what I'm gonna do is I got a bunch of videos, and I'm gonna bring up, wait, I didn't bring up my, wait, let me bring up, yeah, okay. So this is the picture of the photon discussion that I had earlier, and I'm not going to go into this all kinds of detail again. But remember, I was talking about the monitoring of the slits, and so like those are the slits, those openings, and they said they put monitors there. I think I may have the video pulled up. I don't know. Collimations down here on the left, where the curved lines turn into straight lines. I think that's a very important thing to do, because if I have, let's say, a slit that goes from the light area, like I could probably just put like a box here. I could fill it in. I don't know if it fills in or not. I don't think it does. I can go to paint. All right, so like this is the light area, and then over on the right would be the dark area where the spectrometer lives. So I don't know about this opening, going from the light room to the dark room. I don't know about this yet. Even when the light passes through one slit, it creates um, patterns that go outward, and it creates, I think it creates interference patterns. I'm not 100% sure, I can't remember. But it spreads out. Maybe I put a collimator at the location of the slit, a collimation lens where the slit is. I really hesitate to use a lens optic. I'd rather use, I want to use mirrors, and I'll go through a stream with the stuff that I got in that box, and we're going to discover what's in there. Um, because so we pretty much know now if light goes through a lens, it's just going to transfer the information. It's not going to stop there. There's that monitoring of the lens thing, whatever. I don't know about that yet. I get a little bit tongue-tied here. And I've noticed that I listen to some other streams of people talking for like half an hour or whatever, and it puts me to sleep, you know. And I don't blame you if you're like you want to get information. You don't want to just hear a person talking and talking and talking all the time. You want the person to get to the point of what they're doing. Well, the fact of the matter is that there are aspects of this that need to be done in a certain way to affect the most amount of information that you can get using mechanical means. So I'm discussing about that. I'm actually designing and talking about that at the same time. Like, for example, the collimator lens, using that between the light and the dark area. And we got this a-hole trying to say that they want to have you visit a certain location, and we'll just tell you to go straight to hell, and so on and so forth. You have been impolitely banned, whoever the hell you are. So my Nightbot stopped working on Twitch, you know. So I think I can put a collimator lens in there. It would be very helpful, because when you put light through a slit, it's going to spread out. Maybe I need a collimator lens previous. I could actually, well, no. Like when the light first comes into the enclosure, maybe I want to put a collimator lens there. Maybe I don't. Maybe I want to see what's actually there first and look at that picture using the spectrometer as I go along from left to right. Maybe I want to put something in there and see what's happening to the light. But anyway, regardless, the photons have information. I just want to make sure that when they get to the spectrometer, well, that's why you have calibration. You put a light source at the beginning, you run it through its lenses, its slits, its openings, its filters, and all kinds of stuff, and you test the system for information. And so I've got filters, for example, that I want to use to filter out certain aspects of light. I need to be able to do that in order to improve the front end of the system. So if I got a spectrum coming in and I say, okay, I know I have a signal that's at this yellow line. I want to make the signal, but it's a very, very small signal. I want to make the signal brighter. I want to make it look cleaner. And maybe I can even amplify the signal by putting filters in. There's some things that you can do at the front end so that you've got a larger signal to listen to by the time it gets to the transducer. The transducer is an analog device. It has to be a very fast response analog device. A transducer receiving light if you're operating at 1 kilohertz, when you take the inverse of that, it becomes 1 millisecond. So in order to understand what the 1 kilohertz looks like, you've got to have something that is receptive to 0.5 milliseconds of data reception. That's twice the speed that's twice the sampling rate. So that's a wavelength. So 1 kilohertz wavelength is 1 millisecond long. And so you've got to have at least 0.5 milliseconds of resolution. My resolution is going to be better than that. It's got to be like 10 times resolution. Now that's analog to digital. And so far, most of this circuitry is only analog. But if I have a signal coming in at a certain level and so on and so forth, if there's a way that I can amplify and filter out that signal, that noise will go down. It will give me a better signal to noise ratio, and I can amplify that. So, before we get into the actual construction of the box and that sort of thing, I'm going to go ahead and I'm going to minimize that. And we're going to pop open, oh God. I did not. I did. Oh. Oh no, I didn't. It's there. Huh, I thought I lost all my videos. That wouldn't be a good thing. So we're going to listen to a bunch of videos about fiber optic communication. And actually, before we do that, let me bring up Paint again. And I'm not going to, well, yeah, I could probably save it. But let's go ahead and, that doesn't work, does it? I can make a box. I'll make a big box. I don't think it's going to work, is it? Or I could just start a new picture. Yeah, I'll just go File, New, don't save. I'm going to black this out here as quick as possible so we don't get blindsided. We'll use, I don't know what color that, no, that's still not going to work. Let's use this color, no, let's use the red one. So I've got to draw, let's do a line and, let's see. So if you can imagine, what I could do is I just put a line here. So what we're looking at, I could draw another line this way. Now let's go to a different color. Actually, we could go with green. And then we could go with the blue. So down here, it's a little bit, whatever, I guess. There's that. All right, so these are the two sections, and let's see. Let's draw a little box here. We'll just draw this box here. And then we'll draw another one right here. And we'll fill this in. All right. So what I have, that the light section's on the left and the dark section's on the right. The right section has the spectrometer, okay? So I'd like to have a system where I have multiple sources of light. Let's use, I've got different connectors. I've got a bunch of light bulbs. I've got LEDs. I've got all of that sort of thing. I could have, let's say if I use this brown color. Draw this box here. It's actually too big. Let's go back to square. Why that was so big. So maybe I can build. So that'd be like one color. This would be like another color. This could be a third color. And then we could just draw a little circle here. Well, that circle didn't. It's a brown. If I've got a large number of things, so let's say that we've got, let's see, I could do a text box. Size 14. The color's gonna be this one. Oops, I need to have a different type. Use Arial. I'll use which one do I use? I think it's, how about this one? So we've got LED. We've got I've got small incandescent. Well, that's supposed to be orange. And the other one, Let's put laser. I don't have to draw arrows up to the devices because we already know what they are. Well, let's go back to red. We'll draw. Well, that doesn't quite line up just right. Let's use, I wonder if the gray color will show up. Let's see, try this one. Let's try, I'm guessing, so I wanted to take some of the pressure out of the enclosure. I was thinking I wanted it completely to be a vacuum, but that's not going to work. So, which reminds me, let's do another box. We'll paint it blue, and we'll have to use a straight line, and we can use this color here. Now, this is going to be somewhat relative. Oh God, I think I screwed that up. Yeah, I know I did. Let's try that again. What can I make a little box here? No, I could do another text section. We could put it. What the hell? I forgot how to spell vacuum. That doesn't look right. How the hell do you spell vacuum? Like a vacuum cleaner. Okay. So it's. All right, so there's that. There's this line, this freehand. And so I will draw, let's go over here, and we can just say, we got this. And I will just draw like that. All right, and then we're going to use one of the lights And let's do, actually I could do this. I could do white. I could do this one. No, I can't do a trapezoid, can I? I'll just do it with a line. How would I do that? That's not too bad. That almost works. I'll go here, and then we'll use this line. We'll use a straight line to go from here. It should be a straight line, but it's not. And then here. And then outside of the box, we'll use a different colored green. So my thinking, which was, I just thought about this like a few days ago. We take any of the light sources, you know, it's like the orange one, you know, I'll put that line not going all the way up because we don't want to get things too confused. It just gives you the idea of what's going on. So when you have light in the air, it doesn't go, the velocity of light in air is different than the velocity of light in a vacuum. Sound, well, space is a vacuum. Sound doesn't travel in a vacuum. Well, you know, that's really not true because we can bounce signals off the moon. It's actually radio waves. We do get higher frequencies through space. But when you get down to the audio frequencies, they don't travel through a vacuum. You can't hear them. Light travels through a vacuum. But there's a formula. It's called the velocity of light. It's called velocity. And let me see if I can bring up, we'll try to bring up the videos here. And I'm going to drop I'll drop this, and I'll drop, and I will add a web page, and I'm going to look up how, why is Trump in there? Oh, God in heaven. I don't want that garbage in there. Not that he's garbage, but still, it messed up my stream. That was pretty good. Trump, I got a 100% approval rating. Because he popped in and said, "Hey, what up, mofo? Yeah, you all right?" Oh, okay, let's go back. Oh, my God in heaven. I forget that the new tab should be blank. I should do that right now, I guess. What the hell, while I'm thinking of it, you know. It's the settings. Passwords, autofill, oh my God. Privacy, search, tracking, clear browsing data, security cookies. Copilot AI appearance, Pt1 overall appearance, AI new. I don't give a shit about default browser. Start home and new tab page. New tab page. Preload your new tab page. Show home button on the toolbar. No, it's still not working. How the hell do I set that to blank? Ah. Let you son of a bitch, huh? Did I just give you guys my colorful metaphor? It won't let me. Anyway, what the hell am I doing? Alright, so... No, I don't want that audio on that one either. What was I talking about? I was talking about... Oh my god. This is just bugging the fuck out of me now. I have memory issues. Bear with me. We're talking about the light. Okay, the velocity formula. Oh, I didn't want it there. Wait. Oh, that's just a song. I don't know what the hell that garbage is. All right, here it is. Well, they're doing a video, but I want to do it. I don't want a video. Why the hell are they showing me all these fucking videos? Because I'm searching YouTube? Why is that up there? All right, here we go. How do you calculate the velocity of light, speed of light? Yada yada. See. Speed of light. Unit systems. Yada yada yada. Light in the medium. V. The organic chemistry tour. What is this video? Someone's doing the same thing I am. They're using paint to do all their formulas and crap.
Asked to find the wavelength and the frequency of a photon.
Oh, that's
Wavelength
interesting. Wavelength and a frequency of a filter. All right, let me, let's bring up, okay. We'll start with this one, then I'll work back to the other stuff here.
Of a photon that has a frequency of 2.5 times 10 to the 12 hertz.
How does he know that a photon has that frequency? All right, let's just listen to what he's going to talk about.
So what
here.
equation do we need? Perhaps you've seen this one. C is equal to lambda times nu.
What is 10 to the 12? Is that like 250 nanometers?
Now C is the speed of light. Lambda represents the wavelength in meters, and nu is the frequency in hertz.
What? That's supposed to be...
The wavelength is going to be the speed of light divided by the frequency. The speed of light, you need to know it, it's 3 times
That's actually
10
velocity, not
to the
frequency.
8 meters per second. The frequency is 2.5 times 10 to the 12 hertz, which is the same as
that's supposed
seconds
to
to
be
the minus 1,
v.
or 1 over a second.
Well, it just...
So basically, we just need to divide these two numbers.
Yeah. Who's this dude?
And so you can take this number and move it to the top. So you might have some conversions with these problems as well. Just be ready for that. Now let's move. And 100 times 1.2 is 120. Or it could be in a different unit, micrometers. So you might have some conversions with these problems as well. Just be ready.
Alright, so I don't know what he's doing here. Wait just a minute. Let me see if I can find... C represents the speed of light. Lambda is the wavelength. I'm looking for a different formula. This is what I'm looking for right here. Where's the formula? I need to see the formula in a form that I'm familiar with. Velocity factor. So the speed of radio waves in a vacuum, for example, is the speed of light. And so the velocity factor of a radio wave in a vacuum is 1, or a light wave. So a light wave in a vacuum is going as fast as it possibly can go. And so there's that aspect of it, okay? So if we change the medium, we can slow the light down. So outside of that, we've got optical fibers, we've got network cables, RG8, these are different coax cables where the radio signals travel. So normally radio waves travel at the speed of light, but if they're going through a wire or something like that, the wire acts as an impedance and it slows the speed of light down. So then you've got some other formulas that have to do with that stuff. Reciprocal effect, and it's into the medium, usually optical fiber, yada yada yada. All right, so if we go back to my paint box, if I can find it. If we go back to the paint box here, what we're going to have coming out of here is one source, okay? One source. And so what we need to do with this source is we need to split the source. So we'll use a yellow color. I'll use a yellow and that line. I we might be able to use a triangle, I'm not sure. It's not, it's not pointed in the right direction, okay, but well, this is just for demonstrational purposes anyway, okay? This is like a prism. But it's not a prism. What the hell did I call this? I forgot what I called it now. So let's say that light. Let's put this in here. Use the white. I'll put a little circle here. And then we'll put this here. Possible. So I'm actually designing this right now. Okay. Let's go with the line. And we'll go back with the line with the green color. The light comes here. Now we can say for all intents and purposes that we've got a beam splitter, yeah. We've got a light that goes here. And then we've got another light that goes here. And then we'll use this color. I don't like that type. It's too damn bright. Let's try that one. 12. This is a beam. Beam splitter. And now we go here. We can do green text. I can type up here. Calibration wave. And we'll just draw a line from here. So, all right, yeah, we've got to have one spectrometer. I'll just draw a box. I'll make it a different color. This spectrometer is on the side of the box. Let's put it right about here. And then we'll do a text. Now, yeah, I could draw another line between the case. We're going to make an assumption that there's a solid wall. Oh, I don't really want to make assumptions though, do I? Not the prettiest example, but and let's make another circle here. And then a line with a slightly smaller. Oh, why the fuck does it do this to me? You're a piece of freaking garbage tonight. No. I'm not going to be able to get rid of that. I don't know why the freaking line decided to go into 2 to 3 different dimensions, but anyway. There could be filters. I need to put filters. I need to put objects. Um, we could do. Let's see. Let's use this color. Make a box. Make a flat box. So we make a flat box here. That is not a flat box. We go line. And I go outside the screen. And go back to this one. And we'll just make a circle here with this color. Then we've got to make another. We could use this color, and we can go like here. And back to this gray color, text, and then we'll put it here. And we'll use line here. So what the, I probably should go ahead and write that in. All right, so I should save this file, save as, and that's in my pictures section. I'm saving my stuff as Lightwave, L-Wave, so this would be L to A2, Wave 2. Okay, and then we've got filters. Let's make another box over here. Let's see. Let's make a circle. Let's make a line. And then we'll just draw a different color. Make another line. Now, it's supposed to be like straight, so I just put this line here. It didn't look very good, but that's okay. So, yeah, you've got the spectrometer is a separate section. It's, well, actually, what else my arrow here? I got, I don't know why I was having trouble with the arrows before. File. Now, I may have forgotten something. Okay, I may have forgotten something. I need to have, I may be able to fix this. I may be able to fix this. I may be able to fix this. So we got these two beams coming out of the beam splitter, and what I need to have, and this is an absolute necessity, we'll use this gray, actually use a darker gray. And I don't know exactly, what if I used, if I made this into a line, I don't know. I'll just do like this. Screwed up on that mirror. Shit. So this could go, this is a mirror. Calibration and test mirror. And I'm going to draw a line from here. And then I go back here. This one. And then another line here. And then we'll grab this one. No, is it this one? I don't remember. Grab this one. Okay, so yeah, that's not too bad. I made a few boo-boos with the dots that were around the picture, but that's okay. Let's see here. I'll save. So what happens is with this calibration and test mirror is that the signal goes through the beam splitter, and then it goes into this mirror that's rotatable. So let me grab another gray line and just draw a line from here. I don't know if I can draw a circle. I could go freehand. That's not too bad. So let's say I want to calibrate the system. And then it goes through the spectrometer. And then when I flip the mirror, the other part of the beam goes like it goes to the test object. But there's a problem here because, okay, so what I want to do, what I also want to do is I want to send the calibration signal into the dark chamber as well as the test signal into the chamber. That mirror is in the wrong place then. Let's say that that's one idea, but I don't think that's the idea that I want to do. Do I use another beam splitter? I'm going to put another line through here. I'm going to grab, let's grab this color, grab this. See, here the wave's already collimated, but I don't know. You know, something could happen between here and here, and I need to recollimate the beam. I don't know. Let's use this green instead. And then we'll just send this beam. Shit. I screwed that up. I think this is what I want to do. But it's possible, you know, maybe if the beam is split and I send, you know, maybe there's a way to send the uncalibrated waveform. I don't know what the hell is going on. I think I need to send the calibrated waveform straight through. And then the test signal goes down through the bottom, and that goes through. And then I can have a mirror. I could send both of these into a mirror and then swap those back and forth into the spectrometer. But I want to have the option of taking both of the signals and send them into circuitry. The spectrometer, okay, so that's a beam. Let me draw, let's go back here. See, when I do these damn small boxes, I can't make it small like I want, you know? Don't let me. Fuck. Let's go back here. Let's go with the gray. We'll just do, that's a green one again. I'm just thinking, is there a way to run the calibration beam through the test? Would that matter? You know, it's a split beam. Let's put this one. I'm gonna do another circle right here. And this one. Do a line. I don't know about doing an optical phase adjuster. I don't know. You could put other filters in there or something. I don't know. What else? So you've got two signals, and then if I want to run two separate signals, that would be the transducer section, wouldn't it? I'll use this. I go back to the green. And then we go to the orange, which is kind of a little awkward here. Now I'm making this. Get rid of this garbage here. And then do A. Electronic transducer section. I could probably move that down. So this is the secret here. Front end amps. let's do another. Whetstone bridge and front end. So you've got a spectrometer section. Where's this box again here? Paste. There's that. File. Save. So, okay, so a couple of things. The light section has coolers, it has heater, it's got a cooler, it's got a heater. It has to have airflow, it has to have moisture, to get rid of moisture, it's got so on and so forth. So now there's another idea. Let me make this circle and make it blue again. Make this water, or oil, medium. And I'll draw a line from there. Do this again here. File. So we use a vacuum pump. We send the input source lights through a vacuum. Theoretically, that will speed up the light. That will get the light up to accelerated speed. And then probably a good idea would be to make another white circle here, right here, I think. And then go with the line. I didn't know you could do that with the line. So that goes to the case, or it goes through the case or something. I don't know. Let me draw a red one. Let's draw a red one, like right about here. That kind of signifies that that's going through the case. So when it comes out of the collimator, it's going to go back down to the velocity of air, because there's air in that. Now I can use a vacuum inside that case, but it can't be. I could do, let's see. Oops. We want to make that white. Make that low. Actually, let's make that bold type. Didn't work out very well. And then we'll do another one. And call that high. And I'll make a line. And this one. It has to be low because, for whatever reason, I mean, I'm going to seal the cases up as best I can. Let me do another one. Getting a little complicated, but hey, what are you going to do, right? So low vacuums, just to get it a little bit below atmospheric, like 10%, whatever. I'm not looking for a lot. Down in that box where the light goes through, I'll have a much heavier case. I've got some metal cases that I can put together, and that's going to be somewhat interesting. And I can make that more of a higher vacuum to try to speed the light up. I want, maybe it's not going to make any difference, because the light's going to end up traveling through space anyway, and it's going to be going through the air, and it's going to slow right back down again. But at least maybe it gives it a chance, I can't put a vacuum on them cases. I don't know how much of a vacuum I can put on the cases. What time is it? So you've got, this is where the key aspect of all this mess is. You've got the calibrated signal, and you've got your source signal. You got your object signal. You put those two things together, and you subtract out the carrier of the calibrated waveform. Now also, come to think of it, that green arrow is wrong. Let's grab this yellow one. We'll go back to the line. Shit. supposed to be a grating in here. And then we'll just do a line. If you put it too close to that, it does something. Let's put a, let's gonna make a square. A. We'll put down filters. I'll make a line from here. Now, all the actual stuff, like I need to get the design up front so I know what I'm doing and where. I also have two extremely shiny areas on either side of the light section of the project. And what I want to do is I'm going to have light bouncing around in that room between those two sections. Maybe I can actually force reflections back and forth. And I'm not sure exactly how to do that. That's going to be probably something I'm going to have to wing it once I get things built off of that aluminum plate down at the bottom. There's a filter. Oh, wait, let me think. Is it grating? Let me put another line. We'll make it a thick line. Same color. So, where is that line? Oh, shit. Let's use this one again. I'll use a gear. I know what this stuff is because I already got this pre-planned. So the grading adjuster is going to send colors up to the electronic transducer. The filters will filter out whatever it needs to filter out, polarization, whatever. It's got a bunch of crap I got to figure out how to put in there. So I build a spectrometer off the side of the dark room. And I set the, somehow that grading is going to transfer energy from the light source to the spectrometer as well as the electronic transducer section. Maybe I can put in another beam splitter or something. So it'd be a beam splitter, wouldn't it? Where, let me do another, let's see, a gray box. That's filters. It's an orange box like this. Yellow. And back to orange. And type. Might be able to put it right in there. Beam. Beam splitter. I can put an arrow in there. I can make another box. Get rid of this garbage again. File, save. So the beam splitter in this case is going to split the colors, all the colors of the spectrum into two sections. One will go to the electronic transducer section with the filters, and the other will go into the spectrometer. So getting back to what I was saying with the Whetstone Bridge and the front end FET amps. The whole idea is, like I said, you take the main signal plus the signal with the noise, and you combine them, and you get rid of the main signal, and all you've got left is the noise. That's one idea. The other idea is a generator. Let's do this lighter color. Make a box up here. And then make A. Light CW. Generator. Do an arrow. And that goes into here. I fell asleep for like 2 or 3 hours earlier. That's why I'm so late again. So there's two things. So let's go back to here. And we'll put down here in this section here, we'll put down 1. Light CW Gen 2 act as a tuner, and then we'll use this one here. We'll go 2. Only calibration light plus so there's two ways to do the experiment. One is that you take the calibration signal and you add that along with the other signal that goes through the device and everything. That goes into the electronic transducer section. And then you subtract out the CW with the CW generator. The other is, well, actually, you could use the CW as a tuner as well, but it may not be set correctly. You could set it so that it's exactly the same, or you can vary the tuner or something, you know. I'd have to go into a little bit more detail on that on the dark end. Yeah, so one is that you take the same calibration signal and then you split it and you run the split end into a medium to slow down the action of the light and then send it through. But I don't know how it's going to do that, because when you put the light into the object and everything, like maybe you'd have to have a separate area. You'd have to have an enclosed area where that object is, so that the light can come out of the water section. And you could even use an ice cube for that matter. Water or oil medium. Maybe it's got to be enclosed. I don't know. I actually wanted to have the light just bounce around all over the place in that room, but it might be counterintuitive, you know? I don't know. I think it's better to have it enclosed, because then it lessens the amount of total light noise, which isn't really what I wanted to do in the beginning. So I've got a combination spectrometer and electronic transducer section. So when I tune the grating, I can actually see where in the spectrum that it's tuning to see if there's any optimization in the electronic transducer section for any possible signals. The only problem with that is that I think there's a good possibility that I won't see anything in the visible spectrum, whereas I might hear something in the transducer section at a certain light frequency. Which is kind of interesting, because then it would tell me in the spectrometer section that that's where something's located, okay? And then it would tell me the color of the spectrum where I'm getting the noise, even though I can't see it. Then I would have a basis for the filter to go in and switch the filter to clean up the noise coming into that transducer section. It's a good idea, huh? So I'm actually using the transducer section to tell me where in the visible spectrum that the noise is coming from. And then I can put a filter in there. Isn't that crazy shit? No one's ever done this. This is not just some science toy that I'm building. This is something that goes way beyond that. Now when we get back to the whole idea is to be able to change the velocities of light, to be able to change the phase, like I got written down there. The phase is the time it takes. I want to be able to have a time difference between the light traveling from the calibrated wave and the wave that's under test. You would think that there would be that situation because you only have lenses and mirrors and you've got the medium. Maybe if the medium changes the aspect of the information that's coming from the light source, that's a problem. I don't think it will, though, because you're not really observing. You're just sending the light through it. Your final observations in the spectrometer and that electronic transducer section. This fellow by the name of Erland Babcock, he tried to set up a system where he had a tone happening on a speaker, and then he had the light wave bouncing off the speaker, and he was modulating the light wave with the tone from the speaker and using that as a source of noise on the light. So what he was doing is he was modulating the entire light wave with the laser. He was modulating it mechanically. You can modulate a laser electronically, but you can also do it mechanically, and the laser will vibrate. And he claims that he got a signal out of that. There seems to be some kind of aspect between the audio waves and the higher frequency waves of collecting information. What I'm doing with this setup is not that, but I could incorporate that. I could incorporate it in the object under test. I could put a speaker in there. I could even duplicate that experiment that he was doing. And that grading adjuster is an extremely sensitive setup that I want to do. Then it's just the addition of the heater and the cooler, getting rid of the moisture, watching the temperature, and setting everything up on this aluminum plate. Now, theoretically, I'd have to be in some kind of a clean room in order to put this stuff together. You know, I'd have to look at the holder. Maybe I could fabricate the optics out of wood or something. I could set up the holders using the wood instead of the actual optics, and then when I'm ready to put everything in, you know, I could even put in like, I got glass, I've got aluminum foil, I got mirrors. I could put some mirrors in there and just use that as mirror stuff that I don't care about. And then when I'm ready, when I see that everything works, then I put in the real stuff and shove that in there and vacuum it out and, you know, test things. Things got to be tested. I think it's pretty damn cool. This was my dream. This was sort of my dream. I don't know, like, the other thing is I need to make a modulator so that I can transmit my own signal into the light wave to communicate. So whether or not that actually goes into a different dimension is a situation. So I'm guessing if there's a way to make light go faster than the speed of light and send that transmitted signal out, light in and of itself doesn't transfer between dimensions. So there's the theory of chaos and complexity, and if I could create a mirror feedback system, a feedback loop inside of the light box, and create a chaotic system, and inside that feedback loop there's other dimensions that exist in the space between the chaos functions. Infinity exists in there. And so what you got to do is you got to have a signal that goes from 0 to 1 and 1 back to 0. So when it goes from 0 to 1, it passes through infinity. That's a square wave. There's a secret in there. And I'll be damned if I ain't going to find it. Because I know it's there, and I think it's in that square wave. Yeah, I got to develop a feedback system, a feedback loop. Feedback loop. I should put this right down. Let's do white, and then we'll do light. Light feedback chaos system. Like cam to make cam to VCR. I gotta move this. And we'll just draw. And then back to here. Using mirrors, etc. And then we'll use this and that. Where the hell is the line? Why does it do this to me? It's so freaking weird. Now I could also have let's do discolor. Now, this is another thing I didn't think of, is this chaos feedback system. I needed to do this. I wasn't necessarily going to do it on stream, but I don't care. Nobody's going to put this crap together. They don't have the. Nobody has the theory or the knowledge to do this except me. Because you've got to have an understanding of physics and electronics. I mean, there's people that could do it, but they wouldn't want to do it because they wouldn't think that it's just something they need to do, you know? It's complicated, it takes time. Whether or not that chaos system is actually in the system along with the object under test, you know, I don't know. The object under test could also reflect information into the chaos system. You know, that's actually an idea. That's sort of what I was thinking. Now, you might be thinking, well, it's a little bit too complicated, or that's really not part of the original idea of the project. But I have to think of the original idea of how they got all this stuff to work in the first place. When they use audio and radio, they put the two together. In a video sense, or even in an audio sense, you can do the same thing. But we're doing this in video, which is light. And so we're going to use mirrors. We have to use a variable mirror section to be able to control sensitivity, initial conditions. That's a whole another ball of wax right there. So the original idea is to take the video camera, feed it back into the TV to create a feedback loop. I've done it a few times, but I burned up my VCRs doing it. You can do it with a cam and a monitor, and nothing burns out. You can do it with OBS and a camera and feed it back into the computer. You know, that's a little bit defeating the purpose, though, because what you need space. You can't just have it all done in electronic. You probably could. You still, unlike if you do it electronically with the audio signal and you feed it back, there's no space there. And maybe everything's happening too quick. I don't really know. And that space and the way the camera is moved is extremely sensitive. So it's setting up an initial condition in the feedback loop. When there's a lot of noise, it becomes chaos, and when it becomes a good system, then it was able to grab an initial condition to start a pattern. That's where the infinity exists. That's where they claim to have these pictures. They claim this is a true thing. And I believe it because I understand the nature of feedback loops and chaos theory. And I believe that chaos theory is the key to breaking in between the dimensions of time and space because it's there. So how to exactly do that with light and mirrors? So you got a light source. I guess you'd have to bounce the light back into the mirror, wouldn't you? Because that's the source. So you're going from the source, there's no TV screen, but there's between the source and the mirrors bouncing back and forth. And you don't really know which. Also be, yeah, this would be white. So this would be, that would be one of them, and then you could do this one here. Go back over to this crap again. I'm excited about this because this is state of the art. Anything you do with chaos and complexity theory is state of the art. That's where the real fun is. This is a complicated setup. I think this is a better setup than the camera because I'm not looking, I mean, I could look for video pictures, but I don't know how I would incorporate that unless if the, so here's another thing. So that's the setup, okay? And we go back to the videos, I don't want to call it quits. So Lightwave is it's a very high frequency, but it has a lot of bandwidth. What is bandwidth? So when you are on a radio channel, like audio is like, let's say it's 4 kilohertz, okay? But you can't send a 4 kilohertz wave out and expect someone to hear it. You add that 4 kilohertz to a carrier wave. The carrier wave gets sent out on an antenna, and then when the radio is received, the carrier wave is removed, and what you got left is audio. There are different ways to send that audio. You can use amplitude modulation. You can use frequency modulation, which is FM. Pulse code modulation, pulse amplitude. There's all kinds of different codes that you can use in the audio portion of the band that you can add to the carrier wave. All of that stuff gets translated once you hit the transducer section. But the problem and the key is that a small area of light wave contains many frequencies. It's like let's go. We're going to get rid of this. No wait, yeah, that's that, and that's been saved. And I'm going to bring up this. We were talking about velocity and frequency, being able to change the frequency of the light wave, and so on and so forth. I don't really see the formula I'm looking for. I think it was C equals V times F. No, that's not what I want. Has to do with the velocity factor. And our medium is water or oil or something like that. That's a whole different section. You know, you work with that section, you try to figure it out, you know, so on and so forth. What else did I want to get into this? What the hell was I talking about? Bandwidth. So if we change this to calculator, no, we want frequency to wavelength. Calculator. All right, so let's go to 30 megahertz, which is the upper end of the RF band, CBs and stuff like that. I don't know why the hell that's in millimeters. All right, what does this say? 9 meters. Yeah, it's like the 10-meter band. Or the 11-meter band is actually 27. 11 meters, okay. I don't know what this fucking ad is doing here, and I don't know how to get rid of that fucking garbage. Look at all this garbage they have, you know, on this stuff here. Jesus, I can't do this, I swear to God. Frequency in megahertz. Enter frequency, 27. Okay, so now we've got 11 meters, centimeters, millimeters. That's fine. So it's 11 meters. That's a physical length. Okay. Let's go to 900. That becomes 0.3 meters. So the higher up in frequency go, the wavelength is smaller, and you can put more channels in a smaller area. That didn't make any sense at all, did it? In other words, I could put a bunch of 30 megahertz signals on top of that and send it out as a carrier. That's the point I'm trying to make. So when you go to the light waves, you can put, you've got 500 nanometers of bandwidth. Goddamn I need to change that shit, and it pisses me off when that comes up. Wavelength to frequency. All right, so now we want. What? Oh God, I want wavelength to frequency, not frequency to wavelength. All right, nanometers, 500. So you've got, I want megahertz. That's times to the 10 to the 8. So that's a lot of frequency. So you can put a whole bunch of 30 megahertz channels, which is like TV. You could put a whole bunch of TV channels on a fiber optic cable. And then you can convert the TV channel into a 3.58 megahertz a video channel, which is even smaller, you know? So if I were to divide that by 3.58, 6 times 10 to the 8, so 6E8 divided by 3.58. You could put 36 video channels. I don't know if that's right or not, though. 6 times 10 to the 8. 10 to the 6. Divided by 3. 3.58 with 6 zeros. Yeah, I don't know. That's a lot. Let's go watch these videos. Getting way out of hand here.
In your life. It's a game changer for optical communications. Here's the scoop. Optical communication relies on beams of light to transfer data, but traditional methods face issues like crosstalk and signal fading. Enter cylindrical vector beam multiplexing, or CVB multiplexing. Think of it like having multiple lanes on a superhighway just for data. It uses unique beam patterns to minimize interference, thanks to diversity gain. This technique improves bit error rate and reduces communication outages. Imagine streaming a 4K movie with zero buffering or having glitch-free video calls. With CVB multiplexing, we handle massive data more efficiently and reliably. It's the future of optical communication, and it's
AI data centers move data using light. Light travels through tiny devices called modulators. Today's modulators are slow and power hungry. One company invented a special plastic that makes them 10 times faster and uses way less energy. 500 million market cap, up 8x in 12 months. I'm up $2,000 plus 35%. I never sell my winner. I'm Victor the Speculator. Follow me so you don't miss the next one. Lightwave Logic. They don't make chips. They make the material that goes inside them. Think of it like Intel.
Through the optical fiber is straightforward. You keep the LED off for 0 and on for 1. Here I am sending a UART signal from one FPGA to another through the optical fiber, and here you can see we have sent the data. Now sending analog signal like 2 kHz sine wave over here is bit tricky. You need to control the brightness of the LED through the optical fiber in order to send the analog data. So here if you can see I am sending sine wave through the optical fiber. Now this allows for us to send voice signals, since voice signals as well are analog signals. So here I stick my mic into the headphone over here and I will speak and you listen the audio through the optical fiber, which is traveling through the optical fiber.
Hello, hello, can you hear me? This sound is being transmitted. This sound is being transmitted.
Okay, let's talk about that for a minute. So he's modulating a light wave, and it's very distorted. you could say that the amount of audio signal going in as the modulator is too loud. The level is too high because he's distorted. My guess is that if he turned down the level of the audio signal going into the mixer, it would be a lot clearer. He's got the right idea, but maybe he doesn't know everything about what he's doing. But it looks like he knows a lot because he's got all this equipment out here. But there's a lot of stuff. This is a problem. The problem is when you have these boards with all these components on it, you've got more noise than you need. You've got all these things that can interact with radiation, RF radiation, radio waves that's in the air. We're just being bombarded by it. So all them radio waves can be picked up by these little circuits, and not necessarily here when this experiment's doing, but so yeah, it's distorted. Let's see what he says about it.
From the optical fiber.
This is how sound is transmitted from the optical fiber. This board is pretty nice because I can take two of these channels. I can take another signal and feed it into the green, and now you can see both the channels are active. I can couple these using this coupler provided. If I couple these here, I can take this coupled signal, and here you can see both the lights are basically combined here, and you can separate these lights using these WDM filters, red and green. If I put it in the red filter and I insert the output of the red filter here in another optical fiber, I can separate the red from the mixed light. This is pretty amazing. Go and watch the video on my channel where I used these FPGAs to transmit UART signals through this board.
Next video.
Tried to send a secret message to your friend using Morse code and a flashlight. And fundamentally, fiber optic networking works in the same way, encoding data in pulses of light that travel around the world, carrying our phone calls, business conferences, and important internet data. But now hold on a second. How exactly do you send light over great distances and still manage to extract information from it? I mean, fiber optic cables have to carry light for literally thousands of miles, like across oceans. Yet, if you've ever shined a flashlight down a long hallway, you'll know that over any more than a short distance, the light scatters and eventually becomes too dim to make out.
Right.
Well, that is where optical fibers come in. Those really skinny tubes that make your Christmas tree look nice without having to string up any messy lights have some special characteristics that allow them to work over incredible distances. The main way that fiber optics behave differently than your flashlight is that they take advantage of a physical phenomenon called total internal reflection. You see, a fiber optic system doesn't just shine light down any random hollow tube. Instead, optical cables are made up of a core of glass or plastic surrounded by an outer layer called cladding. Both the glass and the cladding have an inherent property called a refractive index, which is basically a measure of how fast light can travel through something. For the system to work properly, the cladding needs to have a slightly lower index of refraction than the core. Now, sometimes this is achieved by using pure glass, that is silicon dioxide, for the core, and then doping the cladding with chemicals to lower its refractive index, while other times the core itself can be doped to raise the same value. Either way, this difference means that if light hits the cladding at a shallow enough angle, it will be completely reflected at the same angle instead of passing through the cladding. That means that it can continue on down the fiber in a zigzag pattern indefinitely. Well, not quite. Although in theory, the optical signal should just keep going all the way until it reaches the other end of the fiber, the pesky real world always has a way of throwing a wrench in the pudding. No matter how high-end and pure an optical cable is, there will always be some imperfections. even if they're so small that you could only see them at the molecular level. And these will cause some of that light to scatter, weakening the signal over distance until eventually it can't be understood by the equipment at the other end. So to combat this, long-distance fiber runs are assisted by repeaters or amplifiers. A repeater gets placed at a point down the fiber where the signal will have weakened significance. Systems now use amplifiers instead. These gadgets have optical fibers which are doped with chemicals that directly amplify light when the weakened signal hits them. Interference to the cables around it, it's common to bundle a bunch of optical fibers, each of which can carry multiple wavelengths.
This is a Lightwave sensor which passes the control signals via this transmitter and receiver ends. Here this is a receiver end which is connected to the computer and passing the values to the computer via serial port, and this is the values passed by transmitter end. Continuously it receives the values of temperature and gas sensors which was connected to this controller and transmitting that via this light signal. So the Lightwave technology works like this. And the total range of this sensor is 20 meters. Here we are using the Lightwave signals with this range. In future we can improve that according to the requirements of the students. Thank you.
What the hell kind of a freaking video was that? Sending data via light. Let's see what you gotta say.
Computer scientist Xia Zhou thinks a lot about traffic.
Problem you see is coming from the increase
Jams. Most of that information is sent by radio frequency, or RF, which just doesn't have the muscle to handle all the computing devices coming online.
Because it's low
radio
bandwidth.
frequency is widely used today for wireless communication. The idea of visible light communication is to look at another medium, which is visible light spectrum.
With support from the National Science Foundation, Zhou and a team at Dartmouth College are developing ways to transmit data using the lighting devices we have in our homes. It's called Li-Fi.
The idea is to turn the lights around us into wireless transmitters to encode data into the changes of the light.
By connecting a small modulation unit, any LED light can be turned into a wireless networking device.
It has much wider bandwidth, and it's also more secure because light cannot penetrate the wall, so you can confine the communication inside the room without worrying about others eavesdropping the traffic.
It can even work in the dark using a system called dark light.
We are generating very short pulses from the LEDs, and they are imperceptible to our eyes, but detectable by the sensors, so they can still transmit data.
Zhou's Li-Fi also receives signals. This technology allows users to interact with devices just by making gestures in the air, which will be handy as devices get smaller. Lights in the ceiling could also sense movements of the entire body. They've tested the system as a virtual reality controller, but its potential goes far beyond gaming.
If the infrastructure, the environment knows the posture of our body, so this can be an input modality to those different devices, so you can interact with them without having any devices on the body at all.
A big limitation of Li-Fi is that light can't pass through walls. That means every light in a house or building would have to be individually connected to the internet. That could be cost prohibitive, at least until wired lights are part of all new buildings. Kevin Enix, VOA News.
Yeah. Okay, what was back over here? Did I see something?
This is a Lightwave
Underwater
sensor
audio and data
which
transmission.
passes the control signals.
Wait.
This is a Lightwave sensor which passes the
I want to listen to that
control
one
signals
too.
via this.
Sorry I was so long-winded earlier. I was designing and talking at the same time. Oh, he sent the light through water.
Let's
but
begin.
That's a laser. Okay, we're not using lasers.
So let's see. For the power source, we are using a rechargeable battery, and for the data transmission, we are going to use Arduino Uno, and from on which the laser is connected. And for the audio transmission, we are going to give the audio input from the audio devices, like we can use the phone, audio player, okay, any devices can give the audio output. Receiver side, we have a solar panel, audio amplifier, speaker,
Did you say
receiving
solar
Arduino.
panel?
Okay, so let's see the working of it. The solar panel acts as the receiving.
Okay, so he's using the solar panel as a transducer. Now, remember I was talking about, there was another video that I went in, that last video. They used a solar panel and it worked pretty good, but the response is not good. You know, the response is poor, but it was better than how they tried to modulate. I don't know what the hell is going on. So this, the fellow that I talked to, Erland Babcock, about stuff, he said the cadmium sulfide cells did not have the response to pick up the light. You can change the LED, you can scruff off the top, file off the top of the LED and use it as a light receiver, which has a much, much better response time than a solar panel. So you would also use a Fresnel lens in front of the LED in order to amplify the light as it comes in. So there's things that you can do prior to the electronic circuitry to amplify and filter the light noise to get, that has to be done. Those are the things that have to be done. You can't just put a solar panel, like I can't do it because I'm looking for something that's way down in the mud, you know?
Device, the laser light falls on the solar panel and the signal is converted into the electrical signal. Okay, the amplifier receives the audio pulses and the output is displayed from the speaker. And the data transmission is done using the Arduino serial monitor. Okay, so whatever signal we are sending some text message, the text message is converted into the laser signal. Laser is turned on or off, and the signal is converted into bit form 0 and 1. And the solar panel receives the signal. That signal is converted into the solar panel act as a. Okay, this is a rechargeable battery, and we are using the voltage regulator for powering of the Arduino Uno that works on 5 volt supply.
Okay, so this is another problem, all right? Number one, he's got way too much circuitry involved in doing this. Now, yes, you can use all of this circuitry, it's fine. He's using it to add the modulation to the carrier frequency and sending it out on the Lightwave. You don't have to use the Arduino and program all this crap. All right, this is just making it fancy and making it expensive. My project cannot have this stuff because all of these items add to the noise in the circuitry. It just adds too much noise. You gotta have the fewest amount of discrete components as possible.
Basically a 5 volt regulated supply.
Even
And
the voltage regulators
the
do
laser
put
light,
out noise.
5 volt laser is connected to the aux cable and Arduino, and we are going to do the switching. These are the switches. If the switches are forward, the device is in audio transmission mode. When switches are backward, the laser signal is sent to the Arduino. Okay, it is connected basically to the Arduino. They are not in data transmission mode. This is the receiving part, the rechargeable battery, power source for the Arduino, and the amplifier circuit for the speaker. Okay, here we are using a solar panel as a receiving device. This is a volume control knob. Okay, this is also the audio transmission and data transmission mode. When in the audio transmission mode, the signal that fall to the solar panel goes to the amplifying device and then to the speaker. When it is in data transmission mode, the solar panel signal is being sent to the analog pins of Arduino from switching.
Now, what surprises me about this setup is using the solar panel. It just seemed better than that other video. This is the second video I've seen using a solar panel to receive the light. All it is but this is all this is. This is a modulated light beam. It's a modulated light beam from the electronics, and that Erland Babcock fella, he bounced the light wave off of a speaker. That's how he modulated the light beam. And how he claimed he got voices off of that. So the voices come from somewhere else and not the laser setup. He got a good idea, but, you know, I felt bad for him. Yeah, what else? Now, sending it through the water, the data rate seemed to be the same, but I think it added more bass. It took away the high frequencies. Yeah,
Is being sent to the analog.
see how that seems to be a higher frequency?
Underwater communication.
So you're losing some of the high frequencies going through the water, which I don't want to lose. It acts like you're losing information.
You can put up text. And we can see the data.
Hey everybody, my name is Paul, W1VLF. Welcome back to the lab. Haven't made a video in quite some time, and I thought this one might be of interest to a lot of different people, because I've been getting questions on some of the short videos that I've done about my optical communications experiments. And I don't know, maybe some of you know that I've been really interested in point-to-point or reflection, and moved to the second location with the receiver to receive the signal and we'll talk about simple transmitters and receivers. 6-degree beam width of the LED array is now that, so is about point. Why aren't you using lasers? And we'll talk a little bit about that. So, eye safety, I think we covered that. We can't see 940 nanometers. The math gets very involved to calculate safe exposure distances, so don't look into them. Handle with care. The array that you'll see, not the 1998 array, but the newer array, the one I showed in the opening, has 140 diodes running 100 milliwatts each at 50% duty cycle. And so safe distance is unknown, but it's not like a laser. Some more stuff here. Practice safe lens at all times. Stay away from the front of the thing. You'll probably be better.
900 nanometers. Was that the UV band or? I got a wrist issue. What's this here? Let's see. Okay, so 400, 700, it's in the IR band. So he's using 900 nanometers, which is in the infrared range. It's a higher wavelength. Yeah, this radio chart is backwards. The higher wavelength is a lower frequency. It's in the IR band.
They're off for it. To give you an idea, typical laser, okay, and you think pointing a 1 degree receiver is bad. A typical little laser module you can buy out of China or wherever for $5, $10 has about a 1 milliradian dispersion. That they don't call it beam width, they call it dispersion. And that dispersion, when you find out what 1 milliradian it is about 0.057 degrees. That's a real son of a gun to point. Okay, it can be done absolutely, but it's very, very difficult. These Vishay diodes are 6 degrees wide, so that's a little bit easier than your 2-foot 10 gigahertz dish. So that works out okay. So let's take a look at what does this 1 milliradian mean. All right, so over here we have a laser with a beam width of dispersion of 0.057 degrees, and here we have the LEDs, the typical Vishay 5490 LEDs. That's wrong. That should be 5940. So that, if you're looking up that number, that is incorrect. It should be 5940, like the wavelength of light we're using. So you point a laser and you go out, what's the distance here? 1,000 feet. 1 milliradian equals roughly a 1 foot diameter. So whatever power you have from this laser, call it 5 milliwatts or 10 milliwatts or 100 or a watt, whatever it is, it has only spread to the diameter of 1 foot at 1,000 feet. That's still potentially, depending on the laser power over here, and the fact that we're dealing with light waves that don't make us blink because we can't see them, so there's no blink response. Those are, that's still, in my opinion, dangerous. Whereas the 6 degree beam width of the LED array is now, that amount of power is scattered into a 100-foot diameter. So the power density is relatively low here at 100 feet. So that's one reason why I don't use lasers, is they're dangerous up close. We don't blink on 940 nanometers. And also, you buy...
Just as a little tip, one of the spyware stuff, they use lasers, they bounce lasers off of a window that you can't see, and that laser reflects back off the window back to the receiver, and it vibrates when people are talking. So you can use a laser pointed at a window and eavesdrop on whoever's inside the house, which is,
a laser. And by the way, this is the detector up here. So essentially it's just a little solar panel with a bandpass filter.
Oh, he's using a solar panel too.
In front of it, one that restricts most of the visible light and only allows the infrared light to pass through. So what happened? Okay. So you're saying, well, I have 140 of these LEDs. How far before they actually combine into a single beam? And you take 6 degrees. Let's see. Let's see. I forgot how far. I guess I forgot to put the distance in between these two. So, but anyway, you can look at, here's one LED and here's another LED, and at some point those two cones are gonna overlap, right? So if you take those same two LEDs and you say, oh, they're 1 inch apart, those two cones are going to coincide at 8 inches. The reality is those LEDs are 0.375 inches away, and they're already half, 50% coaxial, if you want to say that, at 8 inches. So once you move out further and further, they form one beam. You know, it's sort of like looking at I don't know, headlights or some multi illuminator, multi-source illuminator from a great distance. It appears to be gone. But again, removing these 800 and something LEDs, I think my wife thought I was nuts. Well, I was nuts. I'll have to agree with her on that. But that's just a closer look, okay? So let's say this side of the array goes to ground, and this side of the array goes to a 10 ohm resistor in series with the switching voltage that's setting the tone that's on these, okay? And they were in a box, and they were air pressurized. I forget how many amps this drew at 12 volts, but it was considerable. But the power density was very, very low by today's standards. And you could see this. I took these pictures there. And this is the receiver. This was an 8-inch lens. I think I got this from Larry, W-A-N-L-G-Q. Good friend I've known forever and ever and ever, ham radio friend. He got this somewhere, and we made some kind of trade. And just like you'd put a bandpass filter up ahead of your HF rig or whatever, you need to have an optical filter. At least during the day. At night, there's not enough, I don't think, IR to cause a real problem. But if you have to put a filter on this one. But the active area, if you look in here, is only 1 millimeter squared, right? And that has a big effect because it's receiving less noise because it has such a small area. But the problem with having an active area this small is that is aiming. Let's say your lens focuses the energy to an infinitely small dot. Well, when that happens and you're wobbling your receiver around, pointing it back and forth, you've got 5 millimeters square, roughly here, where that dot can fall anywhere on this surface. Damn it. Sorry. Let me go back one. That dot can fall anywhere on this surface here, okay? And it's still going to give you an output. In fact, you won't even know you're in the middle, on the left side, the upper left, the upper right, the lower right. You won't know where you are. All you'll know is you have a 1 degree beam width. Look at the size of this. It's literally 1.2 square millimeters. And now that same infinitely small dot can only walk around this tiny little... Why do I keep doing that? I keep hitting the mouse button. My weak signal source, don't know if you can see it or not, but you see where my mouse is? There's a tiny little white box there. Okay, that's the weak signal source. And the diode is infinitely smaller than that. So what's this? Oh, this opening is about 10 by 10. It's less, but let's call it 10 by 10 just so that we can have, just for the topic, the conversation here, it's not critical. And if you look here is the image projected on a piece of paper. Okay, so look at that square image, and let me go back. That square image is the same size as this. Okay, and why does that matter? Because all of this is noise. All of this is noise. The only thing I really want to receive is this, which is that tiny little dot in the very middle of the barn. That's my weak signal source. It's got a little antenna on it to lock it to my Wi-Fi in the house. Anyhow, but if you go back again and look, this is what's being projected onto my detector, and if my detector is this big, that dot is infinitely small, wandering around somewhere, that light dot, right? So that's why size matters. And in fact, if you put a blocking, make this light go through a pinhole, becomes incredibly hard to aim, but the signal to noise ratio goes through the roof. There's the.
What does he mean by that? The signal, if you put it through a circle. That's interesting what he just said there, and he didn't really explain it. Meaning that if you use a dot, you get a better signal. Because, like, remember with the slits, when a photon goes through, you get all those harmonics. And if you put it through a circle, maybe you're reducing the harmonics and getting a better signal-to-noise ratio.
What is it? The optical receive system without the use of a computer. But if you go up to 16 or 18 or 20 or 30 in there and whatnot, but this is the way I'm going now. I have 4 of these things running. Oh Christ, I can't remember how much from this huge area here, and concentrates it to this part. Then you have an amplifier, and then you run an SDR. Now you can do Q60. Put the big transmitter up there, and this one's on 14.4 kilohertz, and this one is on 17.325.
4 miles, 1 LED.
And I just wanted to make sure. I knew I could hear this one. I wasn't sure what I would hear here. Now, if you look at it in the previous photos or screenshots that I showed, you'll see that there is plenty of headroom. And this isn't even at night. This is, I don't know, LED. Some of the earlier QSOs, a couple of different transmitters here. This is to a valley of minus 70 right here to minus 55, 15 dB, oh, even more. 15 to 20 dB. SDR console allows you to make a signal level strength recording and turn it into a CSV, which you can then plot in
That's
Excel.
another thing, another stream I got to do is I got some SDRs.
So, and I did a little smoothing on this to get rid of some of the QSB, but so, you know, had a SD. Hey, Fred. Not foggy, but very humid.
High school days. This guy lives up around where I live, New England. Optical communication, that was the last one, that was 7 months ago. Laser experience, tile scattering, optical scattering of laser. Cloud bounce. I'm going to grab this. I don't think that's going to come up on there. Oh, wait a minute. I got a project page. Sun noise mitigation for daytime optical communication. Let's see what that's all about. Optical DX. Use a telescope to focus in the beam. Connection diversity. What else crap has he got in here? Oh, he's got a lot of stuff. Saving a wilted tomato plant. Huh. I just put down 40 some odd plants.
Hey everybody, the videos I've done. This is just going to be a quick, like 2 or 3 minute video. I thought this would be a great chance to watch it revive itself after I give it water. So that's all I'm going to say, and take a look. It's kind of interesting, at least I find it that way. Take it easy. W1VLF, I'm out.
Wow, that baby's really wilted. All it did was give it water. Tomato plants are a lot hardier than I thought they were, you know?
A ring that's about 3.5 feet in diameter and about, I would say, 6 inches high. And I'm going to put a chart up for these. They have 5 objects. I'm not sure you can see the first one. It's a thin piece of wire. I think it's number 33. The second wire is using in what they are. That's 1750 wavelengths wide. Better look at. Not really trying to do this in the dark. Let me try this. There's a dead spot, hot spot. And again, you have, now there's a little piece of PVC pipe that's help holding up the wire forward, the piano wire. The sides go up. Okay, both sides. And if it's not in the center, one side gets illuminated and the other side doesn't. And if it's leaning to the left or to the right, one side or the other will go up. Occupy quite a bit of the actual diameter of the laser's exit beam. I'm going to cut the beam in half, if you will, by the laser beam. And then if you look, not really see, there's a tiny pattern there. What I'm going to do now is I'm going to switch off the light. It can go right through that hole. Okay, so I'll put up the sheet right now of the different sizes of materials that I'm going to be using, and I'll put a chart up for these. Tiny little hole I have in the back here, and that way there I don't have to. We'll do this. I will move the laser away from that little hole, and you'll see that it reflects back quite brightly, and I'll get it back through the center of that hole so there's no reflection visible. So we'll start off with a couple of things here. I have, and I'm going to put a chart up for these. They have 5 objects. I'm not sure you can see the first one. It's a thin piece of wire.
Laser.
I think it's number 33.
I gotta call it quits here.
Ed and Renee and those guys are using. I'm using a discrete LED, photodiode, and this transimpedance amplifier. And here's a closer look at that. Okay. The output. Wow, that's weird. Oh, okay. Something's going on in the camera here. This is the output. It's a N connect. SMA goes over to my little AirSpy receiver here, and the input is typically an SMA here, but I've taken the SMA off so that I can get a much shorter connection to the photodiode. Okay, and I'll try to show you this. I'm not sure you'll be able to see it really well. Maybe I'll snap some close-up pictures of this, but the detector sits inside this box, inside this little box, and the reason it sits in there is because it's 100% shielded. The only thing that come out are 2 leads, one to the man, I don't know, I guess it must, right? And a couple of things, let me hold the camera here. A couple of things are happening. If you look at this stick, I hope you can see that. I don't know if you can or not. But this stick shows a square in the middle of it, and that square is the opening of the barn. Pieces of testing. Now I want you to take a look at this signal to noise ratio, and I'm going to put too much bias on it, which means I'm now forcing the diode in well beyond the point where my bias equals the sunlight noise coming from the diode. And watch what happens to that signal to noise ratio. Okay, I'm going to increase it and then we'll walk over. Okay, and it's starting to drop off right now. It's down to 52. Here's a better way to look at it. We'll use the signal saturation. So I'm going to adjust it up. Here's a test. I want to show you this. Here is a extremely bright handheld flashlight, and I'm going to point that right into the lens. Excuse me, not in the lens.
That's a
but
Fresnel
right in front
lens.
of the detector, and see if we go into compression. Okay, that's with that bright flashlight right in front of the lens. Well, what the heck is going on here? Why isn't that causing a problem? It causes a bit of a problem. Actually, that spot right there is where I covered up the optic. They've made some really, really good improvements. And I'm going to jump over to the computer screen now, and we'll go through some of that. Stand by. Well, I'll show a little bit. Okay, so in order to get into the diversity mode, you need to open up the gear menu here, settings, turn on diversity, and set your span to something that you can see. But the important part, and then also, of course, go down here and turn on diversity down here, and then you'll pop open this window here. And you'll see this phasor diagram with amplitude and also phase. So, rotate it. So now we're down, I don't know, 18 dB.
SDR.
A senior member of IEEE Bachelor of Engineering IEEE Photonic from the computer and then uploaded to the FPGA. Then, the FPGA and the driving circuit will drive the 5 RGB LEDs. At the receiver side, the optical lens can focus the light on the CMOS sensor. It is believed that in 2021, the smartphone user will amount to 3.8 billion all over the world. Therefore, the smartphone embedded with CMOS cameras will become the largest optical receivers readily available for optical communication. Optical wireless communication has drawn great attention for various applications, such as high-speed indoor communications and intelligent transportation systems. In recent years, there is an increasing demand for marine resource exploration and environment monitoring. Visible light communication, especially using blue light, has potential applications for underwater wireless communication for its unique advantages over the radio frequency signals and acoustic communications. It can reach tens of gigabits data rates and hundreds of meters. However, the environment-induced impairments, such as the air bubble and turbulence effect, are the most challenging issues for these scenarios. This is a laboratory setup of underwater optical wireless communication affected by the air bubbles. We can see the fluctuation of received optical power. Novel schemes can be proposed to mitigate those impairments induced by the environment and boost the throughput of the VLC system. The system you are looking at now is a Brillouin Optical Time Domain Analyzer, or BOTDA for simplicity. This system is based on stimulated Brillouin scattering, which is a nonlinear effect in optical fiber. The basic principle is that when two optical signals with a certain frequency difference opposite propagating, there will be a power transfer from the signal with higher frequency to lower frequency one.
Clint Eastwood?
That's not my last name.
Those frontal lenses?
Earlier, and it didn't catch.
Okay, well,
they
the
gotta
FCC
be, yeah.
allows hams to use all above 275 gigahertz, and these operate nominally at 474 terahertz, otherwise known as red. And this side is the transmitter lens, or antenna as it were, and this side is the receive. And we have, with 3-watt LEDs, have successfully spanned 173 miles across the Utah desert with two-way voice communications.
That's awesome.
Right, yeah. And
Those are
that was
Fresnel
with, these are
lenses.
10 times as powerful, but we'll be only going a few hundred meters tonight. And since we aren't on the mountain, we will do something silly like point at that flagpole over there or the antenna pole and bounce the light off of that and have another radio over there, and we'll be able to talk to each other without line of sight, direct line of sight. Normally you would do a line of sight,
That's
but we can't do that.
So you're transmitting voice over it?
Voice, yes.
And you got two boxes. One is the transmitter and one is the receiver?
Well, one half is the transmitter, the other half is the receiver. These are both transceiver capable boxes. And they're actually full duplex because when you shoot the beam out, unless there's a lot of dust, the receiver and the transmitter can't hear each other. So we have done many QSOs where we're just standing around talking to each other even though we might be 100 miles apart or something like that.
Oh, that's pretty cool. So is it the glass or is that a focusing lens?
These use Fresnel lenses, which are essentially you take the curved part of the lens and you slice it away because you only need the parts that change. And we use those because they are cheap and flat and light, especially since this had to be, when we did the 173-mile stuff, this was carried on the back of another ham who's behind the camera to the top of a mountain in the dark. I had this one in my car carried on the back of another. We did the 170 light, especially we use those because you slice it away because you only need the, actually you take the curved part of the lens and you slice it away because you only need the parts that change. And we use those because they are cheap and flat and light, especially since this had to be, when we did the 173-mile stuff, this was carried, if you were to think of antenna terms. A few watts of light in, tens of... Delta November 23. Yeah, so we'll do the feedback. There we go. I'm on 550 terahertz, and I think you're on 473, 472.
If you take a solar panel, hook up a speaker to it, and shine a light on it, it makes a little noise, which means we should be able to transmit sound using light. To test it out, I started by making a circuit that amplifies the audio signal from my iPad. Once I pressed play, I can tell the song's playing because the light begins to pulse. This happens because software converts the sound file into an electrical signal that normally goes to the speakers, but in this case, I'm sending it to an LED instead to produce light. And using the same solar panels before, you can see the voltage produced varies right along with the music. So in theory, the flashing of the light bulb carries all the information needed to reproduce the sound in the song. The only problem is that I had to keep the solar panel pretty close to the light. Moving it away even a short distance caused the sound level to drop off, and I really wanted to see if I could use this to transmit sound over a much longer distance. To do this, I had to swap out the LED for a cheap red laser diode, which produced a decent sized dot when I pointed it across my living room and up the stairs. And it actually worked, way better than I expected. Transmitting sound with light. How cool is that? If you take a solar panel, hook up a speaker to it, and shine a light on it, it makes a little noise.
The heck is this paraffin? Holy God. Thermite. What is this here? Is this thermite? This guy's dangerous, ain't he? This guy looks dangerous.
The demonstration I'm about to show you and talk about is dangerous, and you should never attempt it on your own. The test tube on the left contains a few grams of paraffin wax, and something really peculiar will happen when you heat the wax to boiling and then plunge it into an ice water bath. Let me show you what I mean. Here it is again in slow motion. The heat from that fireball was intense. So what exactly is going on here that caused that to happen? I think it's easiest to understand if we take it step by step. First, I had to heat the paraffin wax to its boiling point, which requires a lot of energy. Paraffin's not a pure substance, rather it's a mixture of wax molecules of a variety of sizes, with carbon chain lengths between 20 to 40 atoms long, so it doesn't have a fixed boiling point like water does, but it will start to boil once the liquid temperature goes beyond 370 degrees Celsius. And at this point, the boiling liquid is extremely dangerous. The wax is vaporizing rapidly, making it able to ignite and burn easily as the vapor mixes with the air. And more importantly, the boiling point is well above the auto-ignition temperature of wax. That's the point where it can ignite spontaneously without any spark or flame. So all the wax needs is sufficient oxygen, and combustion will happen. So here's the breakdown behind what you just saw. As soon as the test tube hits the ice water, it cracks, allowing water to come in contact with the hot wax and instantly boil, ejecting the boiling wax upwards. This causes the wax to vaporize, mixing with oxygen in the air and igniting at the spot where there's the most ideal mixture of heat, wax, and oxygen, the top of the vapor cloud.
Shit, huh?
Thanks so much for watching this video. I hope you guys enjoyed it, and put in the comments any questions that you might have related to this demonstration.
Try that at home?
Chose to. Then the way that I use this is to come into class and I tell the students that I have this unusual block that I have found and I would like for them to help and work with me to make some observations about this. I ask them to make a prediction. This block, as we've talked about, orient this. Well, what about if we shine it down from the top on edge? Good, we can do that too. Yes. Ultimately, somebody will say, well, it's probably like a piece of mylar, you know, like maybe those balloons that you have. And we go through that, and sometimes people will say it's a piece of aluminum foil. And I don't say yes or no at that point. I just let everybody make their hypothesis so that we've got all of these different versions that the students can think about. And then finally, at the end of the class, I'll tell them kind of what's going on, or sometimes I'll actually wait until the next day, because if you're doing this several periods during the day, you don't necessarily want the secret getting out so that third period knows what first period did kind of thing. You have all fought that battle before. But this would be an easy process. And then when we're finished, I just simply tell the students, we've worked a scientific method. That's essentially what scientists do. They see something that interests them. They then begin to collect some ideas about it, and they collect data. They might do a little bit of experimentation with that, and then out of that process, they come up with something that they think is a reasonable explanation for what's taking place. So a very easy way to get into that, I don't know about you, but I really don't care to teach the scientific method as though it were some holy process. There are many different scientific methods. They're just methodical ways of learning and getting to know knowledge. And that's all we're trying to get students to do, is to look at this, think about it methodically and scientifically, make observations that are verifiable by others without making hypotheses and assumptions too early in the process. And then after that's finished, then we go through that and we're able to get our hypotheses and finish it up. This is a simple little process. Again, I use it early in my class, and it's something that the students think about from time to time. We're going to start off with paraffin wax, which is used for canning or other types of things. You might want to be careful that when you purchase it, that you get the kind that's found in blocks, because now they do sell some that is in a pellet form, and that won't work for you. We'll take 2 blocks of paraffin, and I've taken and cut a piece of aluminum foil that's just slightly smaller than the block of paraffin. We're going to sandwich that piece of aluminum foil between the 2 blocks. Make sure that the aluminum is smaller than the paraffin, because we don't want any of those raw edges to stick out. Then we have a plate, a Teflon frying pan or whatever that you might have. And I'm just going to take and place this into the frying pan and place it in there for just a quick moment, so that all we're going to do is to heat seal those edges. And this pan is quite hot. It might not have to be quite that hot. And so what we have now is the block, which has been heat sealed on all edges, and as you can see, there's no aluminum foil showing around with that. So a very easy device to make, very cheap. You can use this as a demonstration, or it's possible that you may be able to make enough of these that you could actually do this as an experiment with your class if you chose to. Then the way that I use this is to come into class and I tell the students that I have this unusual block that I have found, and I would like for them to help and work with me to make some observations about this. And so they will begin to make observations like, it's white, and I'll say, good. We continue to make observations about that. Its edge, and so I'll turn it up on its edge, like this. Okay, we can do that too. And we continue to just walk through and look at the different types of ways that we can align and orient this.
Yeah, okay.
I've gotten some comments recently on temperature while also preventing the aluminum from getting hot enough to melt. So I thought it might be interesting to share with you what it looks like when this can's in operation, without any cuts or edits or speeding things up or slowing things down. to be able to go from something that's at room temperature to about 65 degrees Celsius in under 3 minutes. That's pretty impressive. And if you found this interesting, please share it with somebody who also might need a little bit of science in their life. Thanks for watching.
What the heck is thermite? I got a problem with my wrist. Highly reactive pyrotechnic mixture of metal powder and metal oxide. That's some dangerous shit. Ferric oxide plus 2 aluminum. Aluminum and a metal oxide like iron oxide. Iron oxide and 2 aluminum. You mix the two together and you get aluminum trioxide plus heat. Huh. Yep.
What do they talk about on ham? Well, talk about anything that anybody else would talk about. It's like early in the mornings, I can get out to Europe really well on 17 meters, Ukraine, Russia, Saudi Arabia, Africa, and then, you know.
I gotta do one quick. This is the guy who supposedly built the box to talk to spirits from other dimensions.
How many are here, Ty? 40, over 40. Who speaks for everyone? Mary. Mary speaks for everyone. I'm watching the video right now and we're actually filming it, so we'd love to see what you look like. If you could show us your face, we would really appreciate that. You are? A couple of faces coming through. Okay, I'll flip. You ready? Go ahead. That's it. I'm watching now. I'd love to see as many of you as possible in here. See right there? We just got a face.
We did.
Okay, thank you. This was hers. Mary, can you hear me?
What the hell? 11 years ago, no comments. What kind of a rig is that he got up in there? Angels. Angels, sometimes they're not, that's a whole different topic, yeah? Anyway, that's the end of my long-ass stream. SDR, software-defined radios, separate stream, spectrometer, separate stream, chaos and complexity theory, feedback loops, separate stream, setting up of the light waves, separate stream, doing the vacuum of the small section, putting a light through it, and seeing if we can increase the speed of the light. How do you do that if it's like you don't even notice the difference, you know? Yep. Have a good night. Namaste.